Okay, so just like the other classes, the biology and chemistry one, we'll be going over loads of exam questions for physics. It's from both papers, it's from both exam boards as well, AQA and Excel. So we'll get started. We've got quite a few questions to go through. If you've got any questions, you can just drop them in the chat beside as well. Okay, so the good thing about the physics papers, well, for any year 10s and year 11s right now, not too sure about the year 9s, you'll get given all the equations, so there's no need to memorize any of the equations. The only thing you need to memorize is the units and essentially how to rearrange them, but you're given all of them with this. So it's quite good marks getting the physics. They tend to be a higher grade boundary than the other papers just because they're giving you all the equations. You just need to know how to use them and you can get the bulk of the marks. So there's a lot of calculation questions that we're going to be doing today as well. There's questions about the electromagnetic spectrum. So remember the electromagnetic spectrum: radio waves, microwaves, infrared, visible light, X-rays, gamma, I forgot the ultraviolet. And that order, you need to memorize that. You won't get given that. So X-rays and microwaves are both parts of the electromagnetic spectrum. Use the words from the box to complete the sentences. X-rays and microwaves are both, remember there's two kinds of waves. We've got transverse waves and we've got longitudinal waves. All electromagnetic waves are transverse waves. Majority of waves are transverse waves, so that's transverse. In a vacuum, X-rays and microwaves have the same, that's just speed. So in a vacuum just basically means there's nothing in that atmosphere that's essentially affecting it. So the speed is the same of all these electromagnetic waves. X-rays have a higher something than microwaves. We'll think about X-rays are a lot further on the electromagnetic spectrum than microwaves. And as you're going across the electromagnetic spectrum, the frequency is increasing. So this is just frequency. Remember, frequency is how much waves occur per second. So for example, X-rays probably would look like this in a second compared to microwave looking like that. So you can see there's much more waves occurring per second compared to the microwaves. Just write that here. Okay, figure 1 shows a full electromagnetic spectrum. You do need to memorize this as well, even though they've given it here. Figure 2 gives information about four of the types of electromagnetic radiation shown in figure 1. State each type of radiation next to its information. So we just need to choose out of these which one is it. So you need to know the uses of each of these electromagnetic waves as well. For example, X-rays, we use that to look at broken bones and so on. Radio waves for radio, Bluetooth, and so on. Okay, so let's just jump straight into it. So emitted by bright objects and can be detected by the human eye, that's visible light. Visible light allows us to essentially see everything. Emitted by radioactive nuclei and can be used to treat cancer, that's gamma. So even though it can be used to treat cancer, it can also cause cancer as well, so it's both ways. Produced in an aerial and can be used for communication, that's radio waves. Can cause skin cancer in humans and can be used to detect forged banknotes, that's ultraviolet. So remember, ultraviolet is emitted from the sun. That's why it causes skin cancer, penetrates through the skin, alters the DNA, so mutates it, and that's what causes skin cancers. Okay, 2A. A car is being driven at constant velocity. This just basically means constant speed. It's staying the same speed. Remember, velocity is a vector, is speed in a given direction. The driver sees an obstacle in the road ahead. The driver used the brakes to stop as quickly as possible. Figure 3 shows the velocity time graph for the car from the time when the driver sees the obstacle. So the driver saw the obstacle at this point, which you can see, and then this is how long it took for them to apply the brakes. So that's the reaction, essentially. It saw it, and then it applied the brakes. And then after that, it's basically come to rest. Which of these is the driver's reaction time shown in figure 3? So the reaction time is from 0 seconds to 1 second, so just 1 second altogether. That's how long he's looked at something and then he's braked. So it's taken 1 second for that. State one factor that might increase driver's reaction time. So basically, increasing reaction time means it's going to take him longer to press the brakes. Well, if he's tired, it would take longer to press the brakes. So you could say tiredness. I'll give you a few others that you could have wrote down as well, but remember, just only state one if the question says just state one. Another thing you could say is he could be distracted by something, like he could have been on his phone whilst driving, for example. So distraction. You could say drugs or alcohol. That also slows reaction time as well. And you could also say the age as well. So somebody that's a lot older would have a slower reaction time than somebody that's younger. These kind of questions as well do come up in your theory test as well when you practice driving, so this won't leave you. Reaction time and brake speeds and stuff is what you do as part of your theory test as well when you're learning to drive. Okay, so it says calculate the distance traveled between when the driver applies the brake to when the car comes at rest. They've given you the equation here that the distance is the area under the line, basically. So the distance is always area under a velocity time graph, which you should know that anyway, in case I don't give you that. And it says from this point, we're working out the area of this shape, essentially. Now, we know that's a triangle, so what we need to do is we need to find the length of this on the bottom, over here, and the length of the y-axis on top. We're going to times them by each other and divide by 2, or times by half, that's the same thing. So we're finding area of that triangle. Now, on the x-axis, we're going from 1 second to 4 seconds. So the distance of that, all that here, is 3 seconds. So we've got 3 on the bottom. And then the distance going from 0 all the way to here. So we need to figure out what's this point here. Let's figure out the value of one box. So between 0 and 5, 1, 2, 3. So 1, 2, 3, 4, 5. We've got 5 boxes, so each box represents 1. So it's 1, 2, 3, 4, 5. So here we've got 21, 22. So that's 22, all of this here. So to work out the area of that, we're doing 22 times 3 divided by 2. So 22 times 3 divided by 2. You could have also said 22 times 3 times a half. Some of you are used to doing that as well. You'd have got the same answer. Let me put that in the calculator. 22 times 3 and divide that by 2, 33 meters. That's the answer. Okay, so that's area under the velocity time graph that gives you that. Okay, the stopping distance of a car is the thinking distance plus the braking distance. So the stopping distance, basically the distance it takes to actually stop the car is on the thinking distance. So the time it takes for you to think, okay, I need to stop the car, plus your braking distance. So when you actually press the brake, how long will it take for that car to stop? Now, we've talked about what increases thinking distance, stuff like if you're tired, drugs, alcohol, your age. Braking distance depends on like how fast you're going. So if, for example, your car's going at 70 miles per hour, it's going to be harder to brake at 70 miles per hour compared to braking at 30 miles per hour. That's the reason why you have speed limits in place. So you don't so if you say, for example, at a school, the speed limit tends to be 20 miles per hour, because if somebody runs out on the road, it's easier to stop a car at 20 miles per hour, faster, come to a stop compared to, say, traveling 30 miles per hour. That's why they have speed limits in place. Okay, a car has a device that can detect an obstacle in the road ahead. So, of course, if there's an obstacle in the road ahead, then you need to brake, essentially. The device is linked to a computer that can apply the brakes. So it's kind of like, I don't know, like a Tesla, for example, where it can just automatically brake. There's a lot of new cars that can just brake by itself. It is claimed that in an emergency, the computer-controlled car will have a shorter stopping distance than if the car is controlled by a human driver. Explain why this claim could be true. Well, if it's controlled by a computer, there's no such thing as thinking distance. The thinking distance is quicker with a computer than a human. So you need to explain something along the lines of that, the thinking distance is shorter for a computer compared to a human. A human. And then for the second mark, you could just say shorter reaction time overall. So therefore shorter stopping distance. So therefore shorter stopping distance. That's why the claim can be true. So it's claimed that in an emergency, a computer-controlled car will have a shorter stopping distance than if the car is controlled by a human driver. Okay, so thinking distance is shorter for a computer compared to a human because of shorter reaction time. Okay, because I guess a computer can't be under the influence of tiredness or age or drugs and alcohol. So that makes sense. Okay, a different car has a device that could detect rain. Okay. Again, that's in quite a lot of new cars. If it starts raining, the wipers go by itself. The device is linked to a computer that can change the speed of the car. In wet weather, the computer changes the speed of the car. State the change in speed that the computer should make when the road is wet. So if the road is wet, it's harder to brake your car essentially, so it increases by twice the amount. Again, they ask you that in your theory test. So if it's gonna take longer to brake your car, then you should reduce your speed. So in wet conditions, the computer should reduce your speed. So reduce your speed. So a lot of this is quite common sense, really. Give a reason why this change in speed is necessary when the road is wet, because as we just spoke about, it's a lot harder to brake the car. So you would say braking distance would be longer when the road is wet. Yeah. Just out of just again another fact as well. So if the car was ice, and not the car, sorry, the road was iced, so like ice conditions and black ice and such, it would take 10 times the amount to stop your car, basically. So you reduce your speed even further in them conditions. Okay, question 3. A sound wave can transfer information across a room. Now remember, sound waves are longitudinal waves. So transverse waves are the electromagnetic waves. Sound wave is a longitudinal wave. Which row in the table shows what else a sound wave can transfer? So we've got can transfer energy and can transfer air. Well, it can't transfer air, but it can transfer energy. So we need something with yes and no, which is B. Okay, so yeah, a sound wave cannot transfer air. So it just transfers energy. Okay, which of these always increases as sound gets louder? So the louder you increase your sound, your amplitude gets louder. When the frequency doesn't go up, frequency is just amount of waves per second. Speed doesn't change of the wave, and the wavelength is one wave, like the peak of one wave to the next wave, that doesn't increase as well, so it's amplitude. The speed of a sound wave is 330 meters per second. The wavelength of this wave is this. Calculate the frequency of this wave. So the units are completely fine. Remember, frequency is in hertz, which they've given there quite nicely, but again, they don't have to give that. So let's just plug in the numbers. Either you can rearrange the equation first and then plug in the numbers, or you can plug in the numbers and then rearrange. So we've got the wave speed equals frequency times wavelength. So you need to know what the letters mean in this case as well. So wave speed equals frequency times wavelength. So that's lambda, the Greek letter. Wavelength, and this is the speed, so v. So 330 equals the frequency times the wavelength, which is 0.75. I want to get the frequency by itself, so I need to divide by 0.75 on the other side, because that's the opposite of timesing by 0.75. So we're doing this calculation. Putting that in the calculator, 330 divided by 0.75, we get 440 hertz. That's the answer. Okay, moving on. Figure 4 shows a water wave. Okay, so we've got vertical displacement in the water, and then we've got the distance in centimeters as well. So which of these is the amplitude of the wave shown in figure 4? Now the amplitude is from your zero part, not from the bottom, up until the top of the peak, which is here, there. So we need to know what is this over here, roughly. Well, let's work out the value of each box. We've got 1, 2, 3, 4, 5 boxes between 0 and 2. So to work out the value of one box, you would do 2 divided by 5, which gives you 0.4. Yeah, 0.4. So each box value is worth 0.4. So here we've got 8.4, 8.8, and then that's in between. So adding 0.2, that's 9. So it's right in the middle. So is 9 an option there? Yeah, it is. There you go. So amplitude is from the bottom, the 0 part, to the top of the peak. Even if you did the same thing here, you would have got the same answer as well. So as long as you start from the 0 point on the y-axis going upwards, you go to the top of the peak, and that should give you 9. Okay, ripples travel out from the center of a small circular pond to its edge. So ripples meaning, think of if you drop like a stone in water, you end up getting ripples like so, just like this. That's like a ripple coming up. Get rid of that. Describe how a student could determine the wave speed of these ripples. So you know that wave speed equals, so wave speed equals distance divided by time, or divided by time. So you know that from your triangle, this one, DSC, speed equals distance divided by time. So that's the equation we're using. So therefore, in order to work out the wave speed, which you can see from here, we need some way to work out the distance and some way to work out the time. Now, just for the remaining 2 marks, you're just explaining how you're finding these two. So you would measure the specified distance. So you could say use a ruler, for example. And then the time, you would find the relevant time. So find relevant time. So you could say that you could count number of waves in a specified time, for example, to work out that wave speed. So you just need a way to measure distance and time. That's your 3 marks. So 1 mark for stating the equation, and then your other 2 marks comes from saying that you're going to measure that distance and you're going to find the relevant time and how you could potentially do that as well. Okay, so figure 5 shows a duck floating on a pond. The ripples causes the duck to move. Draw arrows in figure 5 to show how the duck moves due to the ripples. Now, if the duck is swimming probably in that direction going forward because it's facing that way, the ripples will cause the duck to move up and down. So think about if you're looking at a duck in a pond, when they're swimming, they look like they're kind of bouncing up and down. That's because of the water waves. So you're just putting your arrows there. Draw arrows in figure 5 to show the duck moves due to the ripples. Yeah, so going up and down, essentially, due to the ripples. Okay, so it's swimming horizontally, but the ripples are causing it to move up and down. Okay, figure 1 shows the circuit diagram. So we've got electricity, which everyone tends to hate. The circuit contains a battery and 2 lamps, and we can see this is a series circuit. So remember, series is just 1, parallel is when it has the lines going through it and it changes what happens. How does the current in lamp X compare with the current in lamp Y? They would both be the same. In a series circuit, current is the same, it's not shared. So you would just say the current in both lamps is the same for both of them. So remember, current is measured in amps. Just put this down here. So current is measured in amps, and it's essentially the amount of electricity that's getting pushed through. The voltage or potential difference pushes it through, and then the current is what's actually going through. Okay, lamp X and lamp Y are not identical. The potential difference across the battery is 4.5 volts. The potential difference across lamp X is 1.5 volts. Calculate the potential difference across lamp Y. Well, in a series circuit, you share the potential difference. So the current's the same, but potential difference is shared in a series circuit. So I'll put that here. So in a series circuit, current is the same. And potential difference, try and not call it voltage, which is quite a common mistake as well. Potential difference is shared. In a parallel circuit, these are the opposite way around. So the potential difference is the same, whereas the current is shared in a parallel circuit. So what did it ask? It said the potential difference across the battery is 4.5 volts. That's how much the potential difference is altogether. And the sum of the potential difference for both lamp X and lamp Y. So for lamp X, I know it's 1.5 volts, which it says here, but I don't know what it is for lamp Y. I don't know what that is. So to work out that question mark, all I need to do is 4.5 minus 1.5. That gives me 3. So 3 volts. And you can check it, 3 plus 1.5 does give you 4.5. So it's shared between both of them. Okay, moving on. So the current in lamp X is 1.2 amps. The potential difference across lamp X is 1.5. Calculate the power. So they've given you the equation. And remember, power is measured in watts. Our units are fine for amps and volts, so we're just plugging everything in. So to work out power, I'm just doing potential difference, which is 1.5 volts, times the current, which is 1.2. Putting that in the calculator. 1.5 times 1.2, we get 1.8 watts. These are quite easy marks, these equation ones, when you don't, especially when you don't even have to rearrange them. But if you do rearrange them, they give you an extra mark for that as well. They tend to become 3 markers. Okay, calculate the resistance of the lamp. So remember, the resistance is measured in ohms. Again, please try and remember the units because they don't always give them. So resistance is potential difference. Always make sure you write your working out with these as well. Don't just stick it in your calculator because you're getting a mark for that working out as well. So the potential difference, which is 1.5 divided by the current, which is 1.2. Put that in the calculator. 1.5 divided by 1.2. We get 1.25 ohms. Okay, the current in lamp X is 1.2 amps. Calculate the charge flow in the lamp in 40 seconds. Charge flow is just, the units are fine, so time has to be in seconds, which it is. If that time was given in minutes, make sure you convert it to seconds. The standard unit for time is seconds. So charge flow is current, which is 1.2 amps, times the time, which is in 40 seconds. So quite straightforward, 1.2 times 40 gives me 48, and the charge flow is measured in coulombs, so that's why the C is there. It's not degrees Celsius, which is what a lot of students think as well. That's coulombs. A switch can be used to turn the lamps on and off. So think about when you're going into a room and you're putting the lights on, you're pressing a switch. When you put that switch on, the circuit's on. When you switch it off, you're breaking the circuit, essentially. Immediately after the lamps are switched on, the resistance of each lamp increases. Why does the resistance of each lamp increase? Well, when you switch the lamps on, the lights are coming on and the temperature is increasing of that lamp, which is why the resistance of each of that lamp increases. So is there something about temperature? Yeah, over here. So the temperature of each lamp increases, which is what's causing that resistance. Okay. Figure 1 is repeated below, so it's just the same one as before, just so we'd have to scroll up. Lamp Y breaks, so this one breaks. What happens to lamp X? Well, lamp X is no longer going to emit any light because the circuit's broken. If you break this part of the circuit, then because it's a series circuit, it's broken. Whereas in parallel circuits, you could potentially get away with that. So lamp X no longer emits light because the circuit is broken. So if you think of your house, for example, when one light breaks inside one room, usually all the lights don't go off in the house unless like a fuse is blown. That's because the wiring usually in the common world is used by parallel circuits. So if something messes up in one room, it shouldn't affect the next room. Okay, moving on. Question 5. Figure 2 shows an outdoor swimming pool. The water in the swimming pool comes from the sea. The water in the pool is heated using a geothermal energy source. Which of the following is a geothermal energy source? So geothermal is renewable. So it's going to be one of these two. So a renewable energy source that uses hot rock underground, or a renewable energy resource that uses the tides, it's the ones that uses hot rocks. Geothermal, thermal means heat, and it's to do with water. So the hot rocks are underground. Yeah, okay, that's fine. And it's renewable as well because you can keep doing that again and again. A non-renewable is if, like for example, crude oil, once you use it, then it's gone. You can't replenish it. Okay, 15 kilograms of seawater is heated before it's added to the pool. We've got the specific heat capacity of seawater. Now, you need specific heat capacity comes up every single year without fail. Like every single physics paper has always had specific heat capacity on it. So please do try and know what specific heat capacity is. It's the ability to heat 1 kg of substance and seeing what it rises to 1 degree Celsius. So you need to know the definition as well. But they've given you it here anyway. The units are fine. So it's joules per kilogram degree Celsius. Calculate the change in thermal energy, which is here, of 15 kilograms of seawater when its temperature is increased by 9 degrees. So sometimes with this temperature change, you might even have to work that out. So obviously in this question, it's quite straightforward. So to work out temperature change, you do the final temperature minus the initial temperature, but they've already told you it's 9 here. So I'll just put that in, times 9. Specific heat capacity we know is 3,800. I'll put that in. And the mass we know is 15 kilograms. All the units are fine. So putting that in the calculator, we end up getting 15 times 3,800 times 9. We get one right here, 513,000 joules. They might even get you to convert that to kilojoules. This might be in kilojoules. If that's in kilojoules, you just divide by 1,000. Any time you see the word kilo, the conversion is always by 1,000, whether you're going smaller by dividing or increasing it by timesing. Kilo means 1,000. Okay, so that's a change in thermal energy. Sometimes you might see this as change in thermal energy like that. Remember the delta sign, the triangle, just means change in. Even this temperature part here as well, you might see change in temperature. It's just the triangle is just change in. Specific heat capacity is usually C, and that's M. So sometimes you might see this equation as delta E equals MC delta T, and you might have to rearrange that as well. So be quite confident in doing that as well. The energy transferred from 1 meters cubed of the surface of the pool to the air is 80 joules each second. The surface area of the pool is 120 meters squared. The energy transferred from 1 meters squared of surface of the pool and there is 8 joules per second. Surface is 120. Calculate the energy transferred for the whole surface area. I guess this is just proportions, right? So if 80 joules each second is 1 meter squared, then to work out 120 meters squared, to get from 1 to 120, you times by 120. So whatever you do to one side, do that to the other side. So 80 times 120 gives me 9,600 joules. Okay, that's how you do that. So yeah, that's just your basic proportions that you need to know about as well. Percentage change is quite a common one that also comes up in this as well. So this proportions one came up quite a lot as well in chemistry yesterday. Okay, so which of the following units is the same as 1 joules per second? This is also very common as well, where they can ask you using units, what are they exactly asking you? Well, if you got joules per second, that per sign means divide. So really it's joules over second. And you should know that joules is energy, because energy is measured in joules, and seconds is time. And the equation which is energy divided by time is power. So you'll get given the equation sheet. You should see on there that power equals energy divided by time. And you know that the units for power is watts, so it's just 1 watt. So you do need to know that as well, how to work out certain things, looking at units and then relating that to the equation sheet as well. So that's just 1 watt. So 1 watt is equivalent to 1 joule per second traveling. Okay. A pool is above sea level. 5 kilograms of water is pumped from sea level into the pool. The water gains 196 joules of gravitational potential energy. The gravitational field strength is this. So remember, it's 9.8 on Earth. Calculate the height of the pool above sea level. So it's quite nice that they've already rearranged it. But again, they don't have to rearrange it. They might give you the equation as gravitational potential energy equals mass times height times the gravitational field strength. So I'll try G. They might give you it like that, and then you had to rearrange it yourself, but it's already rearranged in this case, which is quite nice. We're just plugging the numbers in. All the units are completely fine. Mass is in kilograms, energy is in joules, and then gravitational field strength is 9.8. Do you remember as well, when you've got gravitational field strength of the moon, it's roughly 1.6 as well, so it's lower there, the gravitational field strength. Okay, so to work out the height, we're just plugging in the numbers. Gravitational potential energy 196 over mass, which is 5 times the gravitational field strength 9.8. Putting that in the calculator. 196 over 5 times 9.8 is 4 meters. They've given the units as well, which is quite nice. Okay, the water in some swimming pools is heated by burning fossil fuels. Explain one environmental disadvantage of burning fossil fuels. Well, when you burn fossil fuels, that releases carbon dioxide. So it's combustion, right? So it releases carbon dioxide, and that carbon dioxide is a greenhouse gas, which contributes to global warming. So you'll see quite a lot of overlap between chemistry and physics as well. So it contributes to global warming, because they could ask you this question as well in chemistry as well. So you could have said release carbon dioxide. You could have also said it releases sulfur and nitrogen dioxide, which causes acid rain. Or you could even say that it releases soot, which causes global dimming. So soot is carbon particles, and they're quite dark, and they scatter on the sky, and then it causes global dimming, so darkness essentially. Okay, so you could have said any of the three. So to do with global warming, acid rain, or global dimming. It's probably worth me writing that down because you do need to know about each of them. So acid rain, global warming, and global dimming. Make sure you know this for chemistry as well. This one is caused by sulfur dioxide, or even I'm going to put an X there because the nitrogen, nitride oxides, global warming, carbon dioxide, methane as well, the greenhouse gases, and global dimming is caused by soot, which is just carbon particles. Okay, so make sure you know them three effects from using non-renewables. Okay, question 6. So we've got some isotopes here. So some people used to think that radioactive substances had health benefits, which is not true. They do not. 100 years ago, a company made toothpaste containing the radioactive isotopes radium-228 and radium-226. Now, these numbers here just represent the mass number. So they're both isotopes of each other. Remember, isotopes from chemistry yesterday is atoms of the same element with the same number of protons. So the proton numbers are the same, but different number of neutrons. Okay, so that's what the isotopes are. How are the atoms of radium-228 different from the atoms of radium-226? Well, the neutrons. So if I look at the protons here, both protons are 88, so just the bottom number. Had it been different, it would have been a different element altogether. The proton number defines what that element is. And then the neutrons for this one here is 228 minus 88. So 228 minus 88, which gives you 140 here. And the neutrons here is 226 minus 88, which gives you 138. So you could see radium-228, this has got 2 more neutrons than the other one. I'll just put that there in brackets. Okay, so let's have a look at these statements. Radium-228 atoms have 1 more neutron and 1 more proton. Nope. Radium-228 has 2 more neutrons and 2 more protons. Nope, because there's nothing to do with protons. Radium-228 has 2 more neutrons. Yep, so that's the right one there. Okay, so figure 4 shows the activity of a sample of radium changed over time. Now, these isotopes all have the same graph going down. They will eventually get closer and closer and closer to 0 as time goes on, but it takes ages to get there. What is the approximate half-life of radium-228? Now, to work out half-life, you're just basically halving the activity. So the activity there starts at 200 becquerels. So that's the unit for activity. You just need to half that number that it starts at. So half of 200 is 100. So here's 100. You need to read across the graph. It'd be easier to do this with a ruler, and then read down. So this number that's there, essentially. So what is the approximate half-life? So if I was to choose one of these options, I guess I would choose 6 years. It's closer to 6 years, right? Had this not been an options question, you'd have actually had to accurately read that number. But yeah, it's going from 10, going all the way across and go down. Now, because these are my only options, 6 is closest to where I read down. I just chose that one. Okay. And also another reason as well, if they ask why do you use half-life rather than measuring the full life, because we don't know how long this is going to continue for. It could continue for another 100 years. So we just take the half-life rather than going all the way across. And that's how we compare each of them. Okay, so figure 6 shows a diagram representing an atom. Again, this is chemistry yet again. It says write down the names of particles X, Y, and Z. So we've got the nucleus here, and the nucleus contains the protons and the neutrons. We know the protons are positive, so that's the protons. We know the neutrons are neutral, so that's the neutrons there in the middle. And then finally, in the shells, we've got the negative electrons moving around. So that's the electrons. Okay, I probably shouldn't have put an S on because they're only pointing to 1. I'll just take the S off, just because they're only pointing to 1. The nucleus of a different atom emits a gamma ray. So there's 3 things that you need to know with emitting radiation. So you need to know about alpha particles, beta particles, and gamma rays. Now remember, the particles decreases the number of particles in the nucleus, whereas a gamma ray doesn't affect that. So it says here the nucleus of a different atom emits a gamma ray. What happens to the number of particles in that nucleus? Well, because it's a gamma ray, so just a wave, that doesn't change the number of particles, so you would just say it does not change. So just for D. Okay, so a teacher demonstrates a radioactivity experiment to a class of students. The teacher places a radioactive source in front of the radiation detector. State 1 safety precaution the teacher should take. Well, you want to keep a safe distance from there. There's quite a few different things you could say here. So because it's radioactive, you don't want to keep a safe distance. You don't want to point that source at the people as well. You would use shielding. You would handle the radioactive thing not with your hands. You probably use tongs, or someone use gloves, for example. So any one of them options. Basically, keeping that distance away from the radioactive source. Okay. The teacher uses a detector to measure the activity of the source several times. So you can see they've measured the activity, the first measurement, second, third, and fourth. The teacher tells the class the radioactive decay is random, as you can see from the figures. State how the data supports this statement. Well, the activity values are all different. So you'd say the activity values all are varied slightly. Otherwise, they would have all been the same. So that shows that it's random. Calculate the mean of the 4 measurements. So just your basic math, you're just adding them, and because there's 4, divide by 4. So 21 plus 23 plus 19 plus 22, and then divide that by 4. And the mean you get. Also remember, with these kind of graphs, whenever you're working out a mean and you've got an anomalous result, never include that anomalous result in your mean. So 21 plus 23 plus 19 plus 22, and divide that by 4, we get 21.25. So 21.25. So for example, if I had like, I don't know, a 5th measurement, and that 5th measurement was 125, I'm not going to include that. It'll skew my results quite a lot. So be careful of anomalous results. Figure 9 shows a person on a skateboard at the top of a ramp, and at P, the person is not moving. So he's on his skateboard, he's not moving at P, and then I guess he's going down the ramp, right? The person rides the skateboard down the ramp from P to Q. The gravitational potential energy of the person decreases by 980 joules. So that's the change in gravitational potential energy. Is decreased. The mass of the person is 35 kilograms. That's fine. Calculate H. So they've not rearranged it in this instance like they did in the other one. Calculate H, the height of the ramp, and use G as 10 newtons per kg. So you could see in that last question, they gave G as 9.8. Just use whatever they give you in the question. So we've got change in gravitational potential energy, which is 980. That equals a mass, which is 35, times G, which is 10, times H, which we don't know. Okay, so we could say 980 equals 35 times 10, which is 350, times by H. Now to get H by itself, I just need to get rid of that 350. It's 350 times H, so the opposite of times is divide. So to work out H, we're just doing 980 divided by 350, and that gives me 2.8. So H is 2.8 meters. Okay, moving on. Okay, we've got another one. So the kinetic energy of the person at Q is 950 joules. So where's at a Q? Or towards the bottom. So the kinetic energy that he's essentially gained going down. So remember, kinetic energy is energy caused due to movement. We've got the mass of the person. Again, they've given, it says calculate the velocity of the person at Q and use this equation. So we've got V squared, that's what we're working out, equals 2 times the kinetic energy, which is 950 joules, divided by the mass of the person, which is 35. So there's no conversions need to be done. Had this been 950 kilojoules, you'd have to change that to joules by dividing by 1,000. So 1,000 joules equals 1 kilojoule. So if you were going from kilojoules to joules, you times by 1,000. If you're going from joules to kilojoules, you divide by 1,000. It's worth just keeping the little table there so you don't remember. You do remember, sorry. So V squared equals, putting that in my calculator, 2 times 950 and divide that by 35. We get a really long number. So 54.28571. But we want just the speed. So to get rid of that squared, we need to square root our answer. So we need to do the square root of your answer. So you end up getting square root of answer 7 point, they haven't said to how many decimal places, so I'll just do it to one decimal place. So 7.4 to 1 dp. So 7.4. But do check as well in the question, did they say do it to 3 significant figures or 1 decimal place or so on? But if they haven't, I think it's safe to assume that you can do to 1 decimal place. So you have 7.4 meters per second. Again, they might not even give you the equations like just below. You might have to find it from the sheet as well that they give you in the exam and find it that way. Okay, so figure 10 is a diagram that represents energy changes from P to Q. So you can see decrease in gravitational potential energy. That gravitational potential energy is getting transferred to somewhere. So remember the law of conservation of energy, which says whatever energy you put into something, it has to be transferred to something. It's not lost. So this 980, you can see, is going to kinetic energy, which is 950. And then the remaining, which is 30 joules, because 980 minus 950 is 30, is X over here. It says state what is represented by X. Now, if you think about what's happening from P to Q, the gravitational potential energy, this gravitational potential energy has changed to kinetic energy because he's going down. What other energy is happening as he's going down? Well, there's also a change in thermal energy as well. So his skateboard might heat up. He will also heat up as well. So yeah, there'll be a change in thermal energy, and the reason why it's shown down is because that's wasted energy. So you would just say that it's thermal energy. And another reason why that thermal energy is there as well, as he's going down, there's friction between his wheels and the skateboard thing. So that friction is causes that thermal energy. It says calculate the value of X. We've already done that. It's 980 joules minus 950, which is 30. Because these two have to add up to the 980. No energy is lost to nowhere. It has to go somewhere. Even though it's lost as thermal energy, it's still there. It's still the 30 joules. It says calculate the efficiency of the system represented in figure 10. Well, we don't care about the thermal energy, right? So we don't care about X. It's the 950 we care about. So we're doing 950 over 980 joules, which is put in, and because it's efficiency we're working out, which is a percentage, we times by 100. So if I put that in the calculator, 950 over 980 times by 100, we end up getting 96.939%. You could round that to 1 decimal place, or you could just round it to a whole number, because that's 0.9. Just be specific to the examiner what you've rounded it to. So 97% to the nearest whole number. Okay, so 97%. Okay, so that's 97%. The efficiency. Part D says the person would like to start from P again but have a greater velocity at Q. state two ways that this can be achieved. So how could he essentially get faster down? He could lubricate the wheel, so the less friction that happens, the less heat energy is lost over here. So if you do less friction, there's going to be less heat energy lost, so there's going to be more energy going into kinetic energy. So you could say to lubricate the wheels, and this essentially will reduce friction. Or what you could do is somebody could push him as well. So if you give more energy into something in the start, then he'll go faster as well. So you could say somebody could push him off. Off the ramp. Then he'll go faster as well. Okay, so that's for 2 marks. Again, that was a suggest question, as we saw yesterday as well. It's not something that you kind of learned, but they were saying apply your knowledge that you know and apply it to this question. Okay, moving on. Question 9. 2 people, L and M, have a 100-meter race. L starts running before M, which you can see here. L starts at 0 seconds and M starts 2 seconds later, starts running. And this is a distance time graph. So before we were looking at a velocity time graph, this is a distance time graph. Now remember, with the distance time graph, the gradient of this is the speed. Whereas the gradient in that velocity time graph before was acceleration. So make sure you know the differences between the two. You also need to know this for your maths GCSE as well, not just for physics. Okay, so it says state the distance that L has run when M overtakes. Okay, so at which point does M overtake? Well, this distance over here is when the overtaking happens, right there. So it says state the distance. We just need to read what's the distance at that point. So overtake. So at that point, they've touched point. So he's not overtaken yet. So overtake is when he's actually gone past in distance, which is over here. That's when it's actually gone past L. M has gone past L. So if I read this point over here, it's very tricky to do without a ruler. Okay, so what's each box worth? So between 0 and 10, we've got 1, 2, 3, 4, 5 boxes. So 10 divided by 5 just gives you 2. So each box is worth 2. So over here, we've got 62, 64, 66. Okay, so 66. Now, they would have accepted a range of answers, I think. The mark scheme says allow values between 64 and 68. So they've given you a good range, but yeah, it's when the overtake actually happens. Okay, next question. Calculate the velocity of L when running the 100 meters race. Remember, velocity is speed, but as a vector. So as we said here, the gradient is speed, which is velocity. So I'm working out the velocity of L when running the 100 meters race. I need to work out what's the gradient of L. So it's up to you. You can do the triangle method, or you can choose 2 points and then do change in y divided by change in x. So if I look at L, this point over here, I'm going to choose 2 points. Is it of L I'm working it from? Yeah, of L. So this point over here on L is, let me rub that out. So it's here. Quite tricky to see, is that it? Yeah, okay, so it's that number here as the x at 100 for the y. So 100 for the y. And this over here, well, between 0 and 2, we've got 1, 2, 3, 4, 5 boxes. So 2 divided by 5 gives you 0.4. So each box is worth 0.4, 0.4, 0.8, 2, yeah. So each box is worth 0.4. So over here, I've got 14.4, 14.8, and 14.8 at 0.4. That's 15.2, this number here. Okay, so I've got one coordinate. I just need another coordinate on L. And we could choose, I could even choose that, 0, 0, to be fair. You'll still get the same answer, but I'll choose a number just so you can actually see. So L's a dotted line. I could choose, I could see one at 640 here. So 640. Okay, so what I'm doing is, let me bring these coordinates down. I'm doing change in y divided by change in x for gradient. So for the gradient or velocity in this case, changing y, which we're going to do 100 minus 40, over changing x, which I'm going to do 15.2 minus 6. Putting that in the calculator, I get 100 minus 40 is 60, over 15.2 minus 6 is 9.2. 60 divided by 9.2 gives me 6.52. Continues forever. I'm just going to round that to one decimal place, so 6.5 to 1 dp, meters per second. So that's how you work it out. The mark scheme would have allowed answers between 6.5 and 6.7. So you've got a small leeway there as well. Okay, so part B. A motorcycle is traveling at velocity 6.2 meters per second. That's fine units. As I'm reading this as well, I'm checking the units as well. The motorcycle accelerates at 2.5 meters per second, so we've got the acceleration, until its velocity is 10. Calculate the time taken for this acceleration. So time taken is going to equal change in velocity. Well, it's going from 6.2 to 10. I'm going to do 10 minus 6.2. That's a change in velocity. You might see this equation as t equals change in velocity delta v over a, like so. So yeah, remember that triangle means change in. Over acceleration, which is 2.5 meters per second squared. Putting that in the calculator, 10 minus 6.2, which gives us 3.8 over 2.5. Dividing that, we get 1.52 seconds. Okay, moving on. So you can see, as I'm doing this physics paper as well, how much calculations there are. So you need to be really good at calculations and rearranging and changing units and so on. A motorcycle now decelerates. So decelerates is just a negative acceleration. It's slowing down from 10 meters per second to a stop. So if it's going to a stop, that means the speed is becoming 0. So it's going to a stop. The deceleration is at a constant rate of 4.4 meters per second squared. Calculate the distance of the motorcycle. The motorcycle travels as it slows down to a stop. Okay, so we've got v squared minus u squared. V is the final velocity, whereas u is the initial velocity. So what it started at. Then we've got a times x. So we're finding x. X is the distance. Okay, so you can see here as well how they've given you the symbol equation and not the word equation. So you need to be familiar with using both and identifying what each is. So the final velocity is 0. Have a look. Final velocity minus initial velocity. So the final velocity is coming to a stop, so which is 0. So 0 squared minus the initial velocity, which is 10, so 10 squared, equals 2 times a, which is, because it's a deceleration, so it's because it's slowing down, you have to change acceleration to a minus number, so minus 4.4. And then I'm timesing that by x, which is what I'm trying to find. Let me highlight that so it's explicit. This is what I'm trying to find. Okay, 0 squared, which is 0, minus 10 squared, which is minus 100, equals 2 times minus 4.4, which is minus 8.8, times by x. I'm just going to write it like that. Now to get x by itself, I just need to divide by 8.8 on the other side. So x equals minus 100 divided by minus 8.8. I end up getting divided by minus 8.8 is 880 meters. Now another thing here as well is if you end up getting a negative answer here for whatever reason, just think about what you're working out. You're working out distance. The distance cannot be negative. Displacement can, because that's a vector, but we're working out distance. So just make sure you're just change the sign if you do end up getting a negative for whatever reason. Okay, have I worked that right? Let me just double check. 2 times 4.4 times x. 100 divided by 8.8. Don't know where I got 880 from. I think put it wrong in the calculator. This in the calculator gives me 11.36. I think I typed that in wrong. So I can round that to one decimal place. I'll just say 11.4 meters. Okay, so the reason why I realized my answer was wrong is that number seemed way too big to go from 10 meters per second to a stop, and that deceleration, the number seemed way too big. Just check that you put it in the calculator correctly. Okay, we've got 6 marker here now. So a student has a trolley and a ramp as shown in figure 12. The height of one end of the ramp can be adjusted. So this height over here, you could change it by changing the slope. We've got a trolley and we've got a ramp and we've got points X and Y. The student investigates how average speed, so they're investigating the average speed of the trolley between X and Y depends on the height. So height is what they're changing. So that's the independent variable. The average speed is what they're measuring, so that's the dependent because they're measuring that. And I guess the control will be probably the size of the trolley and so on. So describe the additional equipment the student needs and how the equipment is going to be used to obtain the measurements needed. Now, because we're working out average speed, put the equation down. So average speed equals, you've got the triangle, DST. So average speed equals distance divided by time. And just like that last question, you're going to explain, okay, how can I work out the distance and how could I work out the time that it takes? So the time you could use a stopwatch. So you can use a stopwatch to measure this. So stopwatch, and describe when are you going to use a stopwatch. Okay, so when you start at X and then it gets to Y is when you would stop the stopwatch. That's the time. The distance would be the distance between X and Y, and how could you measure that? You could use a ruler, for example. Okay, so what else are they saying? So measurement of distance using a ruler or similar to find. You also want to take notes as well of different heights. How many different heights are you also going to use as well? And how could you change the height of this? So you could potentially put, like, I don't know, cards to make it higher or something, or bricks or something, or a block, and then reduce it down depending on the number of blocks. So you could speak about that. Measurement of time, so using a stopwatch or so on. So some form of time, and then determination of speed. So your figures that you're going to get, you're going to stick it into this equation, work out speed, and then you're going to repeat it for different heights. And you have to say you have to make an average. So repeat for different heights. And you could even do repeated experiments at similar heights, so then you can work out an average. So that's your 6 marker. You're just working out, explaining that whole process in probably more of a paragraph way than just bullet points. Okay, question 10. What time are we on? Okay, we've done an hour. Data storage computers get very hot. Scientists investigated using the sea to cool data storage computers. The computers are set up inside large metal containers. What you should notice as well with all these questions, they tend to give you scenarios that you've just never seen before, but you're applying knowledge that you know to these scenarios you've not seen before, which probably will come up in the exam as well. Okay, so figure 8 shows the metal container before it was lowered into the sea. So we've got the metal container, the data storage computer is going to be in there, and they're going to put it inside the sea. Why is a container made of metal? Well, metals, data storage, we're talking about like how hot it gets. So the metal container has a high thermal conductivity. It's not an insulator. Metal's not a good insulator. It conducts quite heat, and metal's a poor conductor of thermal energy. No, these two are wrong. It's a high thermal conductivity, meaning that it can it's quite good conductor of heat. Okay, so the walls of the container are solid, and figure 9 shows an arrangement of 6 particles in a solid, so a regular arrangement of them 6 particles. The air inside the container is a gas. Draw an arrangement of 6 particles in a gas in the box below. Well, particles in a gas are not touching each other. You're just drawing 1, 2, 3, 4, 5, 6. So you're just drawing 6 particles in random areas without touching each other, and that's a gas. If it was liquid, so I'll do liquid here. They're all touching each other, but not in a regular arrangement. So you could draw it like that, for example. So liquid, not regular. How does air in the container exert pressure on the container? Okay, so How does air in the container exert pressure on the container? So this is your gas theory. The particles are basically colliding with the wall, which is causing that exerting in pressure. So something about colliding with the wall. Yep, that's this one here. So air particles collide with the walls of the container. When the air particles are hitting that, that's causing the pressure on the container to increase. As the container is lowered into the sea, the temperature of the air in the container decreases. That's the reason why they're putting it in the sea. They don't want the data storage to be too hot. Complete the sentence. Choose the answer from the box. When the temperature in the air when the temperature of the air in the container decreases, the average speed of the particle would also decrease as well. So remember, if you're increasing temperature, then you're going to increase the speed of particles. Particles move faster. So it's opposite. If it's decreasing temperature, you would also decrease the speed the particles are traveling. Okay, so we've got a 2-marker. After the temperature of the air in the container had decreased, the computers were switched on. The computers can cause the temperature of the air to then increase because it is hot, right? So describe how the air pressure in the container changed as the temperature decreased and then increased. So, okay, so as the temperature decreased, so describe how the air pressure, we're talking about pressure, in the container changed as the temperature decreased first and then increased. That's your 2 marks. Talk about the decrease first and then the increase, what's happening in terms of pressure. So as the temperature decreased initially, the pressure also decreased. The pressure decreased. And the reason why the pressure decreased is because the particles are not colliding with the wall of the container. But then as the temperature increases, so the flip side, then the pressure is going to increase because particles are colliding with the wall of the container. So pressure then increases. Okay, 2 marks, 2 points. Okay, so the container has a length of 12 meters. The container has a cross-sectional area of 7.5 meters squared. Calculate the volume of the container. There's your maths. Even if they didn't give you this equation, you should know how to work out volume. It's area of the face times the length. So volume is length, which is 12 times the area, 7.5. Sometimes it could even make you work out that area as well. And you do know like area of a circle is pi r squared. So you would use stuff like that. So volume equals, putting that in the calculator, 12 times 7.5, 90 meters cubed. Again, they might not give you the units. You should know that for volume, it's meters cubed. For areas, it's meters squared. Okay, use a physics equation sheet to answer. So you'd get given the list of all the equations. Write down the equation that links density. So its density is this Greek letter rho. It looks like a P. Mass and volume. So on the equation sheet, you would just look at it. It is mass divided by volume. The average density of the container and its contents is this. So that's the density. So this is the rho value, or the P if you want to call it P. Calculate the mass of the container and its contents. Use the answer to question 5.6. So we worked out the volume here. So we know the volume is 90 meters cubed. So we know volume that we just worked out is 90 meters cubed. We know the density is 1,100 kilograms per meters cubed. The units are fine because both volume is the same in both of them. If they weren't, then you'd have to change it. So make sure you're aware of centimeters cubed, decimeter cubed, and meters cubed for both chemistry and physics. Okay, so we just need to use this equation. So we've got the density, which is 1,100 equals the mass, which I'm working out, over the volume, which is 90. Now to get m by itself, I need to get rid of this divide by 90. The opposite of dividing by 90 is timesing by 90. So the mass equals 1,100 times by 90. Put that in the calculator. We end up getting 99,000 kilograms. And there we go, that's your answer for that one. Okay, question 11. Figure 10 shows an electric whisk that plugs into the mains electric supply. So remember, with the mains electric supply, you need to know the voltage of that. So for the UK, that's 240. The whisk can mix food by spinning a beater. So we've got the electric whisk and we've got the beater. Give two energy stores that increase when the whisk is switched on. Okay, so what energy is there going to be when the whisk is switched on? Well, the beater is going to move. So if it's moving, that's kinetic energy. Another one, the whisk starts heating up as soon as you put the electric motors on as well. So you don't want that heat to be there, but thermal energy also does come out of there as well. So even though it's wasted energy because it's not really useful for the whisk, that also does get produced as well. Okay, so use the equation sheet to answer these questions. Work is done by the whisk when used to mix food. Now remember, work is the same as energy transferred. It's measured also in joules as well. So it says, what equation links power, time, and work done? So you just look on the equation sheet. Power is work done, W divided by T. So remember, power's in watts, work done is joules because that's energy, and the time is just in seconds. So the power output is 92 watts. We've got the joules, which is this. The work done, calculate the time. So we're just using the equation above, P equals W over T. The power is 23,000 equals, oh no, sorry, the power isn't 23,000. That's the work done. The power is 92 watts equals the work done, which is 23,000 over the time. We're working out time, so I need time to be up. I don't want it in the denominator, so I'm going to times by T. So 92T equals 23,000. Now to get T by itself, I need to get rid of that 92. Since it's 92 times T, I need to divide by 92. So T equals 23,000 divided by 92. Putting that in the calculator. 23,000 divided by 92. The time is 250 seconds for that. Okay, so which equation links current, power, and resistance? So you're just looking on your equation sheet and finding it, and it's this one here. If you are in future years, so potentially year 9s, you will have to memorize every single one of these equations, unfortunately. Okay, so the current in the whisk is 500 milliamps. Okay, so that's an issue because we don't want milliamps, we need it in amps. So we're going to have to change units there. The resistance of the whisk is 640 ohms. Calculate the power of the whisk. So we're going to use P equals I squared R, where I is current and R is the resistance. We need to change the current units. So what we need to do is we need to divide by 1,000. So I'm going to do 500 divided by 1,000. So we end up getting 0.5 amps. So to change from milliamps to amps, you divide by 1,000. Okay, now we're just plugging everything in. So power equals 0.5 squared times the resistance, which is 640. So power equals 0.5 squared times 640, get 160 watts. Okay, so let's move on. The whisk has several settings that allow the beater to spin at different speeds. A faster beater speed needs greater power input from the mains electrical supply. What is the potential difference between the live wire and the neutral wire in the mains electric supply? You just need to memorize this, and this is just for the UK. So 230 volts. Changing the beater speed does not change the potential difference between the live wire and the neutral wire because that's just the same for every plug that you put in to the mains. The potential difference is the same. The power input to the whisk changes because the current in the whisk changes. So complete the sentence. When the beater speed increases, okay, speed increases, the current in the whisk increases because the resistance of the whisk decreases. So it's opposite. The resistance is going to decrease when you increase the current and to get the beater speed to increase, because if you want a higher speed, then you're going to have to increase the current because potential difference is staying the same. Okay, question 12. Last century, scientists used evidence from alpha particles scattering experiment to develop a new model of the atom. Again, this is the same content from chemistry about the model of the atom coming across. The alpha particle scattering experiment is when the alpha particles were scattered at the atom, and some deflected back and some went straight through. So in the experiment, alpha particles were directed towards a piece of gold foil. What does an alpha particle consist of? This is 2 protons and 2 neutrons. This is why sometimes they compare it to a helium atom, because the helium atom has 2 protons and 2 neutrons as well. So you might see it as an alpha particle as 4-2, or you might see it as that helium 4-2, like that as well. A gold atom has that symbol. How many neutrons are there in this gold atom? You're just doing 197 minus 79. So the mass number minus the atomic number. 197 minus 79 gives me 118 neutrons. Okay, moving on. We're almost towards the end now. Okay, so the alpha particle scattering experiment led to the plum pudding model of the atom being replaced by the nuclear model then. So remember, the plum pudding model is where it looks like plum pudding. You've got the atom and it's just scattered with loads of positive protons. So that was replaced by the nuclear model that we see today. Figure 11 shows the results predicted by the plum pudding model and the actual results from the alpha scattering experiment. So results predicted by the plum pudding model was that here's your alpha source. If you find alpha particles through the gold foil, that they'll just all pass through. Whereas what actually happened was, so you fired it through. Some particles went straight through, so undeflected, but some particles slightly deflected, and some also deflected at large angles. So there was some deflecting that was happening, which they did not expect, as you can see. So for 6 marks, we're describing how the actual results led to the plum pudding model of the atom being replaced by the nuclear model. You should include details of the plum pudding model and the nuclear model of the atom for 6 marks. Again, this can also come up in your chemistry paper as well. So you're speaking about the plum pudding model first. So the plum pudding model, where the atom, you could even draw it as well for the examiner, the atom is believed to just be a ball of positive charge, and the electrons are just embedded in that ball as well. So just a ball of positive charge. You do need to remember which scientist said this as well. Okay, so that's the plum pudding model. Then the reasons why the plum pudding model was then replaced was because the results, which you can see here, the actual results were not the predicted results. So you would say something along them lines. So actual results were different to the predicted results, which essentially led to the plum pudding model being rejected by doing this experiment. So you would say, what does a plum pudding model say? It does not predict that some particles would be deflected, whereas that's what actually happened. And the large angle of deflection suggests that the atoms contain a nucleus. So that's where the nucleus then came about. So then you could speak about the nuclear model and what it looks like today. So you've got a nucleus, and then you've got electrons going around. So this is what the alpha scattering experiment explained, that the mass is concentrated in the nucleus is charged, and the atom's mostly empty space rather than a ball. So you're comparing the differences between each of them as well. So that's for 6 marks. You just have to explain it on a vast scale and also relate it back to this experiment results as well. Okay, scientists did not know that neutrons existed when they first did the alpha particle scattering experiment. Which scientist did the experiments that provided evidence for the neutrons existing? That's Chadwick. It's not Newton, that's he did forces. Okay, question 13. Figure 1 contains a circuit containing a battery and 4 other components. You need to label the 4 other components. So okay, so this one here is the LDR, so it's a light dependent resistor. So when it's light dependent, essentially we've got a variable resistor here. So variable resistor, so we've got different types of resistors. We've got a lamp over here. And then for this one over here, we've just got a switch. So if you close it, it'll be the circuit completes. If you open it, then the circuit breaks. Okay, the circuit in figure 1 is switched on. The charge of 1.2 coulombs leaves the battery in 4 seconds. Calculate the current in the circuit. So current is just charge 1.2 over 4 seconds. 1.2 divided by 4, which is 0.3 amps. You can see you can get a lot of your marks from physics literally just from these equations as well. So it'd bring up all your marks overall together. So it is definitely worth being quite good with these. Okay, so now we've got magnetic fields and such, which quite a lot of students don't like. Figure 2 shows the shape of a magnetic field around a bar magnet. This is how it looks around the Earth as well. And draw one arrow on the magnetic field line in figure 2 to show the direction of the magnetic field line. They just want you to understand that it's going from north to south. So you could draw it anywhere, but make sure it's going north to south. So say, for example, if I chose this one, the arrow would be that way because it's going north to south. So, and you're just drawing just one arrow, don't draw all of them, but I'll show you what it's like. So again, this way, north to south would be like so. Okay, so on any of the field lines. Draw an X on figure 2 to show where the magnetic field is the strongest. Well, the magnetic field is the strongest where the lines are closest together, which is essentially near the pole. So I could draw it here or here. I'll do it in a big red X. So you could have done it there or there, but just choose one because it says just choose one. Draw an X on figure 2 to show where the magnetic field is strongest. Okay, so give a reason why figure 2 shows the magnetic field is strongest at this point here. It's because the field lines are the closest to each other there. So field lines are closest to each other at that point, essentially, which is essentially close to the poles as well. Remember with magnets, same ones repel, so N would repel, SS would repel. They have to be opposite, so north to south would then attract. Just delete that. Figure 8 shows a saucepan of milk being heated by an electric cooker. Okay, so figure 9 is a table of data about milk being heated. So we've got the mass, starting temperature, final temperature, and change in thermal energy. This might be a specific heat capacity question, I'm guessing. As soon as you start seeing them kind of figures. Using the data from the table in figure 9, calculate the increase in temperature of the milk. So you're doing the starting temperature and the final temperature, you're finding the difference of 40 minus 10, which is just 30 degrees Celsius. They're helping you with the specific heat capacity question, which is why they've done that. So use this equation to find specific heat capacity. So specific heat capacity, I'm just going to call it C because that's what it is. Change in thermal energy, which is 96,000 joules. Sometimes I might have given you that in kilojoules. So I might have said 96 kilojoules, and then you would have to change it to joules. Divided by the mass, which is in kilograms, 0.82. Again, if that was in grams, you have to change it. So that might have been 820 grams, and you would divide by 1,000 to get to kilograms. And I'm timesing that by the increase in temperature, which is 30 degrees. If they didn't help you with this question, you'd have to find the change. Putting that in your calculator, you get 96,000 over 0.82 times 30, which is 3902.439. Continues forever. Just round that to one decimal place or to the nearest whole number. It's up to you because it doesn't tell you in the question. We'll do it to the nearest whole number, but again, tell the examiner you're doing that as well, to nearest whole number. Okay, so there's the specific heat capacity of the milk. Okay, part B. The cooker supplies this much energy in this time. Calculate the power. You've got the equation there. So power, it says give your answer 2 significant figures in this case. So power equals energy, 130,000 over 87 powers in watts or joules per second, if they say give it in that. 130,000 divided by 87, 1494.25 continues forever. They said 2 significant figures. 4 is my second significant figure, and that 9 changes the 4 to a 5, so it's 1,500 watts to 2 significant figures. Okay, so the cooker supplies this much energy, but only 96,000 joules of this energy is used to heat the milk. So essentially the rest is wasted. Calculate the efficiency of heating the milk using this cooker. So efficiency, remember in the last question, they didn't give us this equation and we just had to do it. So efficiency, is useful energy transferred, which is 96,000, over the total energy, which is 130,000. So here it's not saying times by 100. Notice that. So just putting that in your calculator, you get 0.74. But in the last question, we times it by 100, so we got 74%. But here they've said use this equation, so you just leave it as a decimal in this case as well. Okay. Part C. We're almost finished now. So the wiring for the cooker has safety features. Which of these wires should help protect a person from getting an electric shock if a fault is developed in the cooker? So we've got the 3-pin plug in the UK, which they don't have around the world. And in that 3-pin plug, we've got an earth wire, which basically protects a person from getting that electric shock, which essentially would shut off that there. Okay, so about a fuse now. So explain how a fuse can prevent overheating of the wiring for the cooker. So if the current is too large, then what happens is, so that's your first mark, the fuse will break, or you could say melt. So the fuse breaks, which basically switches off the, not the cooker, we'll say the circuit. So that's a bit specific. So the fuse is basically a safety mechanism. So it's that little circular thing that's inside. And sometimes it's like 3 amps, or it might be 5 amps, and so on. So you've got fuses in certain things as well. Okay, final question, and then we'll wrap it up there. So the coil of a copper wire has this mass. The density is this. Calculate the volume. So I'm going to substitute everything in. The units are fine because that's centimeters cubed and that's centimeters cubed. So always check that out. So density 8.96 equals a mass 14.1 over the volume which we're working out. So I need volume to be up. I don't want it in the denominator. So I'm going to times by V. So 8.96 V equals 14.1. I need V by itself, so I need to get rid of that 8.96. So it's 8.96 times V. The opposite of timesing by V is dividing, not by V, by 8.96 is dividing by 8.96. So 14.1 divided by 8.96. Putting that in the calculator, you get 14.1 divided by 8.96. You get 1.573. It's a number that continues forever. I'll just do it to 2 decimal places. 1.57 centimeters cubed. Okay, final few questions. So figure 13 gives information about density of aluminium. So you can see the solid aluminium has a lot higher density, so mass per volume compared to the liquid aluminium. That's expected. Explain the difference in density of solid aluminium and the density of liquid aluminium in terms of arrangement of particles. So you're just describing the difference between solid and liquid. So the density in a solid is greater than density of liquid, and I explained the reason why. The fact that the distance between particles in a solid, so distance between particles in a solid is less than distance of particles in a liquid. Just gonna write it like that. Okay, so it's just that particle theory of thinking how the solids and liquids look, essentially. Okay, so a student boiled some water. They boiled some water. Calculate the amount of thermal energy needed to change 60 grams of water to steam at its boiling point. The specific latent heat of vaporization of water is this here, and use this equation. So all we're going to do is the 60 grams is not in kilograms, so we need to change that to kilograms. So we're doing 60, this M here, 60 divided by 1,000 to change it to kilograms. We're then timesing that by 2.26 times 10 to the power 6. That's going to give us Q. So putting that in the calculator, we end up getting, to be careful of that, that was quite a sneaky conversion that they put in there. Q equals 1.36 times 10 to the power of 5 joules. Okay, moving on. Okay, final 6 marker that I'll discuss and then we'll wrap up there. A student is investigating the melting of ice. Okay. The student has crushed some ice in a beaker at a temperature of -20 degrees Celsius, so it stays as ice, I guess. The student then heats the beaker and its content for 20 minutes. Here's a graph, so you can see every time there's going to be a state change. So -20, it's ice, and then to 0, you could see there's a state change, so it's probably changing to liquid at this point. So then it stays as liquid, and then after 100 degrees, there's another state change. So anytime there's a flat point here, so this flat point over here, change in state. Over here, there's also change in state there as well. So from here, it's going from a solid to a liquid, and then from over here, it's going liquid to a gas, because 100 degrees Celsius is the boiling point of water, and 0 degrees Celsius is the melting point of water. That's just where water just exists, right? So for this 6 mark, use information from the graph, describe the changes that have taken place in the 20 minutes shown in the graph. You should refer to data from the graph. So I guess the time points where all these changes are happening, and the state, solid, liquid, or gas of the contents of the beaker. So just what I described there for 6 marks. So you talk about ice melts at 0 degrees Celsius, you would say water boils at 100 degrees Celsius, and you would just say the time of where this is all happening from. So from 0 to 1 minute, so 0 to 1 minute, at this point over here, the temperature of the ice is rising from -20 to 0. And then from 1 to 7 minutes, so this point over here is where the ice is melting, so that's the state change. And then from 7 minutes onwards to this point over here, the next thing is happening, and then again the state change between these points here. So you're just reading the time on the graph and explaining what's happening at each point as well. Okay, so I'm going to wrap it up there. I'll get the recording sent out. Hopefully you found all the classes this week quite helpful. All the recordings are up. You should have all the notes for each of these as well, so I'll get that sent out as well now. But thank you for joining.